For the next 3 examples, we're going to look at using factoring to solve trigonometric equations. Once again, when we look at these equations, we want to think about them in the algebraic form. So if we see sine squared and sine, let's think about that as being like a variable from algebra. So let's think about minus 2y squared. Since we have sine squared, we'll think about it as variable y squared equals 3y plus 1. So in algebra, if you were going to solve that equation for y, the first thing that you would try is to get everything on one side and try to factor. And it doesn't matter what side we bring everything to. So I'm going to go ahead and bring everything to the right hand side and get 0 on the left hand side. Alright, now we're going to try to factor what we have. So this is similar to 2y squared plus 3y plus 1. So if we were factoring that, we would split it up as 2 parentheses, and we need 2 sine x and sine x. The signs are both plus, so we'll put plus, and then 1 and 1. And we could always check that by foiling it back out. Now that it's factored, now we're going to do what we would have done over here once we factor. We're going to set each of these factors equal to 0. Once we do that, now you notice that we have an equation, 2 separate equations, where sine x is raised only to the power of 1. So now we have 2 linear equations, or equations in linear form, and we can actually solve by getting sine x by itself in each of these linear form equations. Subtract 1 from both sides. So we have 2 sine x is equal to negative 1. And then we will divide both sides by 2. So we have sine x is equal to negative 1/2. What 2 angles would those be? We look in quadrants 3 and 4 where sine is negative, and we're looking for what angles have a sine value of negative 1/2, and that's the y values on the points on our unit circle. So we have 2 places. We have 7 pi over 6 and 11 pi over 6. Remember that we're looking for all of the angles in radians from 0 to 2 pi on the entire unit circle. And here we're going to subtract 1 from both sides as well. We end up with sine x is equal to negative 1, and we want to know what angle has a sine value of negative 1. And for the entire unit circle, there's only one place where sine is negative 1, and that is when x is equal to 3 pi over 2. So we have 3 solutions: 7 pi over 6, 11 pi over 6, and 3 pi over 2. We want to solve the equation tangent squared x plus tangent x minus 2 equals 0. And we're looking to solve it over the interval from 0 to 2 pi, which means that we're working in radians. And we're also asked to solve for all possible solutions. So let's start by thinking about tangent x as being like a variable in college algebra. So this would be the same thing as like u squared plus u minus 2 equals 0. The first thing that I would try if I was solving that in algebra would be to factor. So let's try the same thing here. Set up our 2 parentheses. It's already set equal to 0, so all we have to do is factor this trinomial. We can think of it as tangent x, so u times u, or tangent x times tangent x. And the numbers that we have to choose from at the back would be negative 1 and 2, or 2 and negative 1. So we have opposite signs, and let's say -1 and +2, and if we FOIL that back together, we should get that original 3 terms. So now that it's factored, we're going to set each of those factors equal to 0. And then solve the linear forms of each of these equations. So +1 + 1, we get tangent x is equal to 1. -2 - 2, we get tangent x is equal to -2. Now, working with our unit circle, we're looking for tangent x is equal to 1. Tangent x is equal to 1. We're looking in quadrants now 1 and quadrant 3, and we're looking for the places where x and y are exactly the same. So remember that tangent x is sine divided by cosine, or y divided by x. And if I take the y value and I divide it by the x value, if those x and y values are the same, then we get +1. So we are describing our 45-degree reference angle family. So 45 degrees, or pi/4 radians, into quadrant 1. So our first solution for that angle we'll call pi/4. And then in quadrant 3, that's the 5 pi/4, that's our pi/4 reference angle family going into quadrant 3. Since negative divided by negative will give us that +1 that we want for tangent. So we get 5 pi/4. So let's list out those two solutions. So we have pi/4, 5 pi/4, and we actually have one more equation to solve, and this is a tangent value that we're unfamiliar with. We know that we're going to be looking in quadrant 2 and quadrant 4, because that's where tangent is negative. So we're looking for angles in quadrant 2 and in quadrant 4. So keep in mind that we always look in 2 quadrants, both quadrants, not only where tangent is positive and with those familiar reference angles, but also where tangent is negative in both quadrants, and then even angles that are maybe unfamiliar. So let's look at tangent x equals -2. Well, we don't know that, so we're going to put that into our calculator using our inverse tangent function. We're going to feed it the tangent value and let the calculator tell us the angle. So the angle that we get when we put this into our calculator, make sure calculator is in radian mode. We're working in radians. And the value that we get is going to be a little strange looking, but that's okay. It's in radians, and it should come out to be a negative value. If you remember our discussion for the inverse tangent functions, tangent inverse will spit out an angle from quadrant 4, and it's going to think of those angles as being negative angles. So what we get is expected. We get -1.107148718. So there's the entire angle that we get in radians, and that's an approximation from your calculator. Well, we don't want this because this is not within our interval. Remember, the interval that we were looking for down here was from 0 to 2 pi. Well, this is a negative value, and the negative value would be less than 0, and that does not fit in our interval. So let's think about where this would be on our unit circle. So I'm going to come up here. I'm going to draw a little separate circle up here. Okay. This is definitely in quadrant 4. We're going to start here and think about a negative angle in, let's say it's about right there. So this would be -1.107, etc. for that angle. And this is not the angle that we want. We want an angle that's coterminal to this, that lives in the desired interval from 0 to 2 pi. So let's add 2 pi to this. Now if we add 2 pi to this, we actually get an angle that lives within the interval that is coterminal to this. So we're describing the same angle, except instead of thinking of it as a negative angle, we're going to go from here all the way around to here, and we're going to consider that to be a positive angle. So when I add 2 pi in my calculator, I get 5.176036589. Okay, so there's that angle. There's one of our solutions. Now, we have another solution. Remember that tangent has a value of -2 in quadrant 4, but also in quadrant 2. Now, how do we determine what that angle is? Well, the reference angle that we used, the amount that we went from the x-axis into quadrant 4, this will be called our reference angle. And we want to go the same amount from the x-axis into the other quadrant where tangent is negative, also into quadrant 2. So we're going to go up that same exact amount and determine what angle this is in quadrant 2. So we're going to use that same reference angle of -1.107, and we're going to go that amount from the x-axis into quadrant 2. And we want to figure out what that angle is. I'm going to do this one in green. Okay, so we want to know what this angle is here. So it has the same reference angle as that angle. But we're going to know if I start here and I go in the positive direction and I stop at that point right there, what angle has a reference angle? What angle in quadrant 2 has a reference angle of -1.1? Well, in order to find this angle, let's think about what we're working with here. If I did a half rotation, that would be a radian value of pi, but we don't want to do a half rotation. We want to stop just this amount short of a half rotation. So we're going to subtract from pi. So we're going to say pi minus that reference angle 1.107 148,718. So when you put that in your calculator, subtracting off that reference angle from pi, then we actually get this angle in green that we want, that quadrant 2 angle, that also has a tangent value of -2. So that angle would be 2.034443936. So we get 2 more solutions for this equation. They look kind of weird, but that's okay. So we're going to write those 2 down as 2 more of our solutions. So we have 5.176036589, and then the quadrant 2 angle. Okay, so these are our 4 solutions that we found that fit in the interval from 0 to 2 pi. Now if I want all possible solutions, there's we talked about the long way of doing it and the short way of doing it. The one way that I could do this is to add 2 pi in to all 4 of these angles. Well, there's a shorter way to do that for this one. If we notice that the angles pi over 4 and 5 pi over 4, these are actually directly across the circle from each other. They're 180 degrees apart, or pi units apart. So we're going to take the smaller of those 2 angles, and we're going to add multiples of pi. And this would be the more efficient way of writing them, instead of just adding 2 pi, 2 pi, 2 pi in to all of those. And then this will always happen for tangent. If you notice, these 2 angles are actually 3.14. If you were to put these in your calculator and subtract them, your answer would be approximately pi. So if you take this smaller of these 2 angles, so we'll take the smaller radian value, if you were to add pi to that, then you would actually get the quadrant 4 angle, 5.1, etc. So what we're going to do is we're going to just add multiples of pi into this one as well. So this would be the more concise way of doing it. Keep in mind that you could also take all 4 angles and add 2 pi n to all 4, and you would also have all possible solutions. Anytime that we can write it more efficiently than we want to. When you're working with tangent and cotangent and tangent have periods of pi, which means that they repeat themselves every pi units, so we will always be able to write tangent in the more efficient way by just adding pi n to the smaller of those 2 angles. In this example, we see that we have 2 trig functions. We have secant and tangent within the same equation. The first thing that I want you to do is I want you to think about this in terms of the algebra. So each of these trig functions, we're going to think about them as a different variable. So we have secant squared. Let's think about secant as being like x. So we'll say x squared. And let's think about tangent as being y. So we have something similar to this if we were solving equations in algebra. The first thing that we want to try, especially if we have 2 different trig functions, is to attempt to bring everything over to one side and factor. So let's try that first. And if that doesn't work, then we can try something else. But let's first try to bring everything over to one side and factor. So let's subtract 2 times tangent theta from both sides of the equation. So minus 2 times tangent theta equals 0. Now, if I was doing this in algebra, if I were to subtract and set it equal to 0, what do you notice is common between those 2 terms? Well, they have a common factor of y that we could factor out. Here we have the same thing. We have a common factor of tangent theta. So let's bring that tangent theta out to the front, and what we're left with on the inside now is secant squared theta minus 2 is equal to 0. Once we have factored as much as we can, we have 2 things multiplied together that gives us 0. We can set each one of these factors individually equal to 0. Now what we see is that we actually have now 2 separate equations. Now each one of these equations only has 1 trig function, which is what we want. So now we have tangent theta equals 0, and that's basically already solved how we want it to be solved. All we need to do now is to determine what angles describe this. Tangent of some angle equals 0. Well, remember that tangent is y over x. In order for that fraction to be 0, what would have to be 0? Well, in order for y over x to turn out to be 0, it doesn't really matter what the x value is. We're looking at something that has a y value of 0. So points on our unit circle that have a y value of 0. That would be right here at 0 degrees and 180 degrees. So we're working in degrees, just to remind us there. So 0 degrees and 180 degrees would be places where we have tangent values of 0. Okay, so we got that one done. We have 2 angles now for our solutions. Here we need to solve by using the square root method. We have the quadratic term, we have the constant term. We do not have a linear term. So I can solve using the square root method by adding 2 to both sides. And once I have that secant squared equation by itself, we can take the square root of both sides. And remember that when you take the square root of both sides, you have to put in the plus or minus. So we have secant theta is equal to plus or minus the square root of 2. Now, sometimes it's hard for us to remember what angle has that secant value of plus or minus the square root of 2. So we can always think about it in terms of the reciprocal function. So the same angle that has a secant value of plus or minus square root of 2 has a cosine value of that same angle as the reciprocal of that. So that same angle also has a cosine value plus or minus 1 over the square root of 2, which if we rationalize that, it looks really familiar, square root of 2 over 2. And we can see very easily quickly that that's our 45 degree reference angle family. So 45 degrees into quadrant 1, 45 degrees into quadrant 2, 45 degrees into quadrant 3, and 45 degrees into quadrant 4. And we're looking at all 4 quadrants this time because we had that plus or minus. So we're looking at 315 degrees, 225, 135, and 45 degrees. So we actually end up with 4 solutions. And all of these have a secant value, either plus or minus square root of 2, and also a cosine value of plus or minus square root of 2 divided by 2. So we end up with actually 6 solutions from 0 to 360.